In this video, we will demonstrate the Xilinx Artix-7 FPGA GTP transceiver, the industry's only transceiver in a low-end FPGA that offers auto-adaptive equalization, non-destructive 2D eye scan, and IBIS-AMI simulation models to simplify high-speed serial design. Let's quickly go through the challenges that you may be going through today. Designing serial interconnects is only getting more complicated as rates increase. As frequencies rise, channel impediments become more impactful. Channel loss, for example, grows significantly as rates increase. Similarly, stubs, connectors, and impedance mismatches all have a greater impact at higher rates. While transceiver features can compensate for these impediments, having the tools available to analyze and optimize your system is an important component to a successful serial design. The Artix-7 GTP transceiver brings you both. Let's look at what we mean. First, let's look at the quality of the transmit signal. Here we have a 6.6 gigabit per second signal driving into an Agilent DCA-X, giving us a nice open eye with only 28.4 picoseconds of total jitter over this nominal amount of trace and cable. We can produce a similar result using the IBIS-AMI models and Agilent ADS software, ensuring that our simulation is accurate from the outset. This simulation uses S-parameter models for the cable, an approximation of the trace for the channel, and the GTP IBIS-AMI models set with the same transmitter settings we use to drive the scope. This is just the starting point for simulating the whole channel. Since this is a bit simple, the next step is to add in some additional trace via this trace board. This is 26 inches of FR4 material, which should add some significant losses. By adding the S-parameter model to the simulation, those losses are easily visualized. The eye is now almost completely closed. These types of losses are not atypical in today's systems, so we've enabled the GTP with an equalizer built to handle them. The auto-adapting automatic gain control and continuous time linear equalizer circuits optimize themselves to match the incoming data, resulting in the most margin possible. Fortunately, the IBIS-AMI models of the GTP also replicate the auto-adapting circuitry, giving us a look at the margin we can expect after the equalization is compensated for the channel. It looks like there's plenty of margin in the simulation, but we have to verify that the hardware matches these results. The GTP has the ability to scan the incoming payload data and generate a two-dimensional eye without interrupting the incoming data. This is done via a secondary sampler that is offset from the data sampler in both voltage and time. By comparing the primary data sampler to the secondary sampler, we count the number of times that they're different and count the number of errors at each combination of voltage and time offsets. Importantly, this is done without disrupting the data path, allowing Eye Scan to operate on payload data at runtime. The hybrid design currently loaded into the Artix-7 can control this capability of the GTP and display the eye for us. All of this area in the middle represents error-free performance. Lots of margin here. We can compare the simulation results to the hardware measurement, and it's apparent that the simulation accurately modeled the performance of the GTP transceiver in the system as a whole. Simulations are key to ensuring that your system has the margin you expect prior to receiving hardware. By delivering IBIS-AMI models that are capable of accurately simulating the auto-adapting equalization features of our transceivers and the eye scan capabilities in silicon, Xilinx enables you to guarantee and verify the performance of your system. To see how well Xilinx transceivers will work in your design, please go to xilinx.com/transceivers.